Them keep on disturbing. Yeah lah. Okay, let's continue. Okay, so there's one part which is actually been taken out from your syllabus, which is actually the basic of semiconductor diodes. Right? The previous syllabus whereby they actually taught what is a P type and N type of semiconductors, but for the current syllabus they went directly to the transistor. All right, and they went to into the diodes. They didn't teach the basic of the diodes. That's why you guys are confused actually. All right, how does diode works, the how to say, the applications of diode, and then how does the transistor works. Okay, one good thing is that we don't have logic gates anymore. All right, so we don't have to play around with the AND gate, NOR gate, and all that. So we're going to focus on this three parts in the middle here. All right, front part, the cathode ray oscilloscope, we have the semiconductor diodes, and we have the transistor. Now, for cathode ray oscilloscopes, I'm going to be talking about the term ionic emission. All right, I'm not going to go into the CRO structure. That one I'm going to pass it to you guys because we only have today's less than 2 hours lesson to actually carry out regarding diodes and transistor. And my main focus for you guys is actually more on the diodes and transistor instead. All right, so term ionic emission. Now, the word term ionic emission actually comes from the two words which I previously mentioned 2 weeks ago. All right, the word term ionic can actually be breaked into two. All right, whereby term actually comes from the word thermal. Thermal meaning means heat. All right, so ionic actually comes from the word ion. All right, so term ionic emission is actually the emissions of ions, or to be more specific, negative charges, negative electrons, okay, which is ions lah, okay, and due to a heated metal surface. So the heat is actually whereby there is thermal energy. All right, there's thermal energy from it, and term ionic emission means the emission, the release of ions, which is the electrons, from a heated metal surface. So this is where the term ionic emission comes from. All right. So how does term ionic emission comes? It's a very simple structure like this. Just need a 6-volt power supply connected to a heated filament cathode. All right. And this heated filament cathode, usually it has very low resistance so that the current can actually pass through. All right. It needs to be able to release electrons out very, very quickly. Okay, so how does term ionic emission occurs? It's actually a metal consists a large amount of electrons, all right, which are free to move around. Okay, when it's free to move around at room temperature, the electrons are free to move, but they still remain in the metal. Normal cases, when if this is an open circuit, all right, the electrons are actually able to move in the metal. That's a usual thing, all right, but it cannot escape from the metal. If you were to remember what I mentioned regarding the photoelectric effect, all right, photoelectric effect is whereby the electrons in the metal, they actually absorb the light energy, and if the light energy is sufficient, the electrons will actually come up from the metal, and if it has more energy, it will actually move away with high kinetic energy. All right, so for same thing for term ionic emission, the electrons actually can move around in the metal as usual, but they don't have sufficient energy to escape from the metal surface. So where can they get this energy to escape from the metal surface? It is actually when the switch is on, current starts to flow through, but when it reaches this filament part, it has high resistance, which is high. That when the resistance is high, which means it will actually lose in terms of heat energy. The electrical energy get converted to heat energy. All right, and that heat energy or the thermal energy will be absorbed by all these electrons, and they will escape out from the metal surface. So hence that is actually how term ionic emission occurs. All right, the release of electrons, because the metal is heated at high temperature. All right, and some of these electrons gain sufficient energy to escape from the metal. So term ionic emission is very similar to photoelectric effect, all right, whereby they are both happening in the vacuum. All right, let's see. Okay, they are both happening inside this particular vacuum glass, but for photoelectric effect, we need light to come in and hit on the metal surface. But for therm ionic emission, all you need is actually a 6-volt alternating current power supply. Actually, even if it's not alternating current, it's direct current also sufficient. All right, it doesn't have to be alternating current. It can be a direct current, but you just need a mere 6 volts for the current to actually start moving the circuit. This part, all right, this is the filament. The filament is different from the wire connecting from the power supply to the filament. All right, the filament part is similar to our light bulb. All right, the main reason we have the light over there. All right, but the only thing is that this filament heat up very quickly. It converts the electrical energy to heat energy and allows electron to be emitted out from the metal. So when the electrons emitted out from the metal, there'll be electrons moving freely around this whole entire cathode ray as oscilloscope. Okay, so that is actually what the 6-volt power supply is meant for. Okay, so if I'm talking too fast or anything, please do let me know. We already have currently 35 people. All right, 1/3 as usual. Okay, so what else do we have? We have this extremely high tension. All right, I'm going to go to your textbook for this. Question, can you guys hear the sound of the fan? Can you hear the sound of the fan? Okay, good. Very little. Okay. So at least the noise cancellation is good. To those who just came in, hi. It's not fair, you know. You guys are seeing my face and I'm not seeing yours. Not fair. Continue on eating, Erica. All right, okay, let's look at your textbook. Okay. So for a textbook, actually, it's similar to what I had just now. Okay, but first thing first, all right, you need to know that we have two power supply. The first power supply is located here. All right, this is the first power supply. This 6-volt, always remember the 6-volt power supply is to emit electron. All right, its main purpose is to release out the electron. Then we have extremely high tension. EHT stands for extremely high tension. It's usually 2 kilovolts to probably 12 kilovolts. All right, so it's 2,000 to 12,000 voltage of power supply. So that's why it's called the extremely high tension, and usually EHT is more used by teachers as demonstration. They won't actually use it for students to carry out the experiment themselves. Okay, so right. Now, when the electrons has been emitted out by all this tungsten filament, what will happen is actually we have this extremely high tension power supply. If you look at the extremely high tension power supply, this is negative terminal. All right. So this negative terminal, this is also direct current. Please do take note. Okay, this is also direct current. So this negative is connected to this metal, hence the metal is a cathode metal. And then the other positive is actually connected to the anode metal. All right, so this metal is positively charged. This one is actually negatively charged. Now, it is very important this part is negatively charged. Why? Because this all the electrons emitted out from the tungsten filament are negatively charged. So when they are negatively charged and they reach this cathode, it will actually cause repulsion. Repelling, they will have a repulsive force between the cathode and the electrons. And then another thing is that this anode is positively charged, very highly positively charged. So all these electrons, which is negatively charged, is attracted by the positive plate, the anode plate. Hence, they will accelerate. All right, the electrons will accelerate towards the anode. Okay, when they accelerate towards the anode, they have high velocity, or what we call as maximum velocity, and they will have kinetic energy as well because they are accelerating. If they are accelerating, which means that their velocity is increasing, and hence they have kinetic energy. All right, so this is where we accelerate the electrons towards the anode part. All right, so this whole entire cathode ray oscilloscope needs to be carried out inside a vacuum chamber. All right, it needs to be carried out in a vacuum tube. Main reason is because electrons are negatively charged. When they are negatively charged, they will be easily attracted by other particles if it's not vacuum. All right, if it's attracted by other particles, they will not go in a straight line towards the anode. They will start going in a zigzag form. All right, just like how you guys are going to the canteen, all right, during recess timing. Why you have to walk in a zigzag path while your friend is here, someone is in front of you, so you walk in a zigzag path. All right, but if there's no one blocking you at that path from your classroom over to the canteen, you will walk in a straight line directly towards the canteen, isn't it? All right, so that's the main purpose of why we need to have the term ionic emission at the vacuum tube. All right, so up to here, are you guys all right? Okay, so for cathode ray, also this term ionic emission, able to understand? All right, good. Now, let's see what else do I have to talk about this. My Xavier is here. All right, do you mind if I skip through this? Are you guys all right with this? Or do you need me to explain this part? Need or no need? Or can I go to the N-type and P-type semiconductor? All right, give me one quick minute. One minute. All right, my auntie is here to help me. Okay, now the next part of this whole entire structure. Okay, I'm going to take this out. Let's play with simulation shortly. All right, now, so this is actually a cathode ray oscilloscope, okay, whereby I'm going to pause this first. All right, this yellow color metal here, this is actually connected to the 6-volt power supply. This is actually where we allow the term ionic emission to occur, all right, at this particular part. And then after that, this blue color is the cathode, and the red color is actually the anode. That's why you see the negative and the positive here. This too is actually connected to the extremely high tension power supply. Now, remember one thing, this part main purpose is to accelerate the electrons. The 6 volts main purpose is to the 6 volt is actually to release out the electron. The extremely high tension over here is meant to accelerate the electrons. Why accelerate? So that it can actually move in a straight line. Then you would notice that there are 2 more parallel plates over here, like what you have in the textbook. These are actually the deflection plate. Now, this deflection plate only got one set, and this is placed above and below. Okay, so this above and below is similar to the purple color one. All right, it's similar to the purple color one, whereby its main purpose is actually to cause the cathode ray to actually move up and down. Okay, so if there is two plates, the purple color one is actually the y-axis deflection. The blue color cyan one is actually the x-axis deflection. So when I start this, all right, the purple color line will actually cause it to move up and down, but the blue color line will actually cause it to move left and right. All right, so that's the main purpose. How does it actually cause this to happen? Because number one, okay, let's go back to the slides. Okay, when switch S1 is closed, electrons will be emitted out from the power supply, from the filament. When S2 is closed, that means the circuit is complete for the extremely high tension power supply, the electrons will actually shoot in a straight line towards the screen. Usually the screen is located here. Okay, so when the screen is located at this position, okay, we have a switch S3. Okay, this switch S3, if you notice, is actually placed on the y-axis. Electrons are charges. All right, electrons are charges, and electrons is actually moving from the negative terminal towards the positive terminal, and current will actually flow from positive towards negative. This is from chapter 3. Okay, so what happens is this electron negatively charged, when it actually passed through this deflection plate and switch S3 is closed, complete circuit for the deflection plate, this part will be positively charged. Why is it positively charged, in case you ask? Main reason is because here the extremely high tension power supply over here, this is positively charged plate. The bottom part is negatively charged plate. So this plate at the top will be positively charged. So what happens here is that the electrons, being a negative charge, will be attracted towards the positive plate. And hence, that's the reason why, all right, when S1 is on, S2 is on, and S3 is on, the electrons actually deflect upwards towards the positive plate. Because the electrons are negatively charged, it will be attracted towards the positive and repelled by the negative plate. That's why it actually curves upwards. All right, and if you switch the terminal, all right, if you switch the power supply for the deflection plate, whereby the bottom part is positive, the electron's cathode ray will move towards the positive plate. Okay, so this is actually for the deflection tube. Deflection tube, okay? Okay, so I'm gonna go next to the Maltese cross tube already right now. So it will be alternating current depending lah. Alright. Coba again, sorry. Cathode ray got application in our daily life. God. Shreya's question I'll answer shortly. Eject, cathode rays application number one, my time lah. It was a TV. Last time, before the flat screen TV, before the LED TVs, before the plasma TV, it was actually a cathode ray TV, whereby when it's a very big, huge bulb, okay, and then when we switch on, the first thing that we see is a single dot. And then after a certain period of time, it will start to warm up, and that's where the whole entire picture comes out. All right, so that was my memory of a cathode ray oscilloscope. The second application that you would notice, all right, bye, see you. Drink water, ah. Bye. 乖乖 ah. All right, the next application, yes, IU, the big TV. The next application, if you look at this, what does this look like to you guys? This simulation right now. Yes. In the hospital, to detect the heartbeat sensor, it actually uses a cathode ray oscilloscope. That's why they didn't flatten the whole entire sensor. The sensor is still such a big box over there because it's actually using a cathode ray. But nowadays, yes, there is actually they made it smaller and smaller. All right, last time it's actually the cathode ray oscilloscope. Okay, all right. Back to Shreya's question. Uh, will it be alternating current? Actually, it is alternating current, or else they wouldn't have this going up and down. All right, it is alternating current. That's the reason why it can actually deflect up and down towards left and right. All right, only alternating current will allow it to switch. Is if it's not alternating current, it won't switch at all. Okay. All right, so we will continue with the Maltese cross tube. I'm sorry if the tempo is a little bit fast for you guys, but I have to go fast. So if it's too fast, later when I get this recording up on YouTube, then you guys actually go back and slowly watch it lah, huh? Okay, now this is actually a Maltese cross tube. When, let's just say this is actually where the electrons are being emitted out, it has already been accelerated, okay? So what happens here is that if there is, the Maltese cross is not here, it will actually be a green color light, okay? Because this green beam is actually the cathode ray. But if the Maltese cross is actually situated at this part, all right, if it's blocking, what happens is the cathode rays are actually when it's being accelerated. I repeat again, when the cathode ray are accelerated, when it hits the screen, it will actually turn fluorescent. Okay, so the main reason why it's green, it's because the cathode ray actually hits a fluorescent surface. I remember it's somewhere here. This one. Let me just find mana into screen. Okay, when I see it, then I'll let you guys know. Now, when S1 is turned on, S1 is actually where the 6 volt is located. When the 6 volt is located, all right, S2 is actually still off. All right, S2 switch 2 is off. The accelerator is off. The cathode and anode plate is actually off. Only the electrons are being emitted out from the filament. What happens here is that the light from the hot tungsten filament is blocked by the opaque object, which is the Maltese cross. It actually forms a shadow, but this light is actually still a white light, the normal white light. Okay, but when you switch on S2, all right, when S2 is on, S2 again reminding you guys, S2 is actually here, the accelerator between the anode and the cathode. Okay, so S1 main function is only to release out the electrons from the filament. S2 main purpose is to accelerate the electrons. All right, it's for acceleration. When it accelerates, it will hit the screen. when it hits this fluorescent screen, it's actually a material that is actually being placed on the screen. All right. And that material, when it actually hit by high kinetic energy electrons, it will start to glow fluorescent. Okay. So that's the reason why when switch S1 is on, but the extremely high tension voltage is off, there is no green color beam. But when S1 is on, there's a green beam over there. All right. The cathode ray produces a fluorescent effect on the screen. All right. This actually shows that the cathode ray possesses momentum and kinetic energy. So please put a remark over there. Okay, because I remember seeing this question before. So I've forgotten which year already. Okay. So do take note, when there is no extremely high tension, all right, S2 is off, it's just a normal light with a black color shadow. But if there is, all right, the electrons released out is being accelerated, then when it hits the screen, it will become fluorescent. It will have that fluorescent effect because the cathode ray or the electron beams has momentum. They converted the kinetic energy to light energy. That's why it has the fluorescent effect. All right. But now, what happens when we put a magnet bar on it? Okay, this one I think I need to screenshot this thing and then to take it out over to the PowerPoint slide. Okay, so I'm going to focus on this right now. Now, how do we see where the shadow is going? Okay, remember the green color beam is actually produced by high kinetic energy electrons. So at the tube, all right, let's reduce this size a little bit. Sorry, my head a bit haywire right now. Okay, now when S1 is on, S2 is on, S1 on, electron starts to come out. Okay, electrons will start to come out. When S2 is on, it will actually accelerate in a straight line. Okay, now electrons are actually moving towards the screen. This is electron. Again, electron move from negative terminal towards positive terminal. So that's the electron movement. And when electron move, current will be created. All right. Current is actually the rate of charge flowing. So the charge that's flowing right now is the electrons. So what happens here is that when electrons is moving from negative towards the positive, which in this case is actually moving from the left side of the cathode ray tube towards the right side of the cathode ray tube. This is the electron movement. The current will move in the opposite direction. So I is actually moving towards the left. All right, that's one thing that I want you guys to think about right now. So the next thing is they brought a magnet bar close to the fluorescent screen. Okay, so if I were to draw the view from the front of the Maltese tube, the current, I'm going to focus on the current, okay? Electromagnetic electromagnetic chapter 4. All right, from the front view, I will see the current is actually entering, so I will see a cross for the current, and then they brought a magnet which is the north towards the cathode ray. So they brought a north over here, and magnetic field is coming out from north going into south. So this is the direction of the magnetic field. Current is entering the page, magnetic field is pointing towards the right. There is current exist in this situation, so we have to use Fleming left hand rule. All right, we have to use Fleming left hand rule. So what happens right now is taking out your Fleming left hand. All right, so FBI. Right now, the current, the middle finger needs to enter the paper, and then the magnetic field is actually pointing towards the right hand side. My thumb is actually pointing down. So if you, all of you can try this out, current pointing into the multi, for me is pointing into the screen because that's where I'm drawing my picture right now. My magnetic field is pointing towards B. All right, the arrow of magnetic field pointing from north to south, and my thumb automatically point downwards. So this is the direction of the force. That's the reason why, for this situation case, the shadow actually moved down. All right, the shadow moved down because in terms of a cathode ray, the electrons is actually moving from left towards right, but the current is moving right to left. So from the front view, we see the current entering I into the page. When I into the page, you bring a north pole closer to this side, the magnetic field will actually be pointing towards the right hand side. And using the Fleming left hand rule. Why left hand rule? Because there's current already. There's charge moving. All right. So that's the reason why we use Fleming left hand rule. And the force is actually pointing downwards. Our thumb is pointing downwards. So that's the reason why the shadow actually moved down. Okay. So let's go back to your slides. Okay. That's the reason why the deflection of the cathode can be determined by the Fleming left hand rule. So if they switch the north pole and the south pole, then the shadow will actually go where? The green color shadow will actually move up. All right, when they move it up, main reason is because now the magnetic field is actually pointing towards the left hand side. If they switch the terminal of the S, the north and south pole. Okay, up to here, are you able to understand this? Shreya? Rest okay? Getting there. All right. Okay. I am going to go to semiconductor diode. Semiconductor diode, I have to use this slides. Now, this slides I gave you guys before, in case you guys didn't notice, it's actually inside the resources. Right, these slides are actually inside the resources. I think somewhere at the top part. This one is something that I gave you guys very, 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 very early. There. Electronics. Alright, it's inside the resources group, so please make sure have a look over here. So I'm gonna tag this for you guys. Alright. So you can actually open up the notes to find out, to see it even clearer over there. Alright. So I'm gonna go, I want to talk about diodes. That's the main thing that I think you guys are confused with. Alright, here. Now, semiconductor diodes. Let me get my simulation out as well. I'm sorry if you can hear backgrounds. Where is my pure diode? Silicon, yes. Okay, while they open up. Now let's talk about diodes. Now, semiconductor, the main reason we have our whole entire technology advancement right now that I previously mentioned the other day during the bank guild. All right, our main reason why we have all this electronics around us right now is because they found semiconductor, and this semiconductor that they found is actually more importantly the pure semiconductor they found was actually the silicon. All right. Why? Because when they created electricity, they know that there are two types of metals. All right. We have the metal, which is a good conductor. A good conductor is whereby they allow electricity to pass through because they have a lot of free electrons that moves inside the metal. All right. So the resistance of metal are generally very low. But one problem is resistance is actually resistivity length over area. Now, when the temperature increase, it will cause the resistivity to increase. And when temperature increase, it will actually cause resistivity to increase, and hence it will actually cause the resistance to increase. Okay, so in this case, when the temperature increases, the resistance increase, the current that flows in the circuit will actually drop. Now, if you would notice, when you learn chapter 3, when you were learning regarding electricity, it actually obeys the Ohm's law. Then when you went to learn electromagnetic, right, it doesn't really follow the Ohm's law. Main reason is because in electricity, we were focusing on direct current only. But for electromagnetic, or to be more specific, for electromagnetic induction to happen, we actually need alternating current. And this alternating current actually, how to say, they don't really obey Ohm's law that much. So that's the reason why when you were dealing with transistor or the electrical power generation, all right, the whole entire country's electricity generation, when the resistance increase, the potential difference increase. But then the current over there, the formula doesn't really fix. Okay, so main reason is because of whether we are focusing on direct current or alternating current. Now back to here, metal. Metal over here is going back again to the general one, which is actually following Ohm's law. All right, so metal is a good conductor of electricity because they have free electrons and the resistance are generally low. I just noticed that I wrote a lot of things wrong over here and no one corrected me. How come? All right, temperature increase, resistance increase. When resistance increase, okay, I cannot use this. No one telling me that I've been explaining things wrongly already. Yeah. Now, resistance of metals is generally low. Yes, which is true, but I forgotten. Betul lah. When the temperature increase, the resistivity. I'm talking about temperature increase. The resistivity will increase. Resistance increase. At high temperature, the current will start to drop. And this is actually not a good thing in our era of technology because when electricity runs, when our handphones have power, it will start to heat up. All right, when you use your handphone after a certain period of time, it will start to heat up. And when it heats up, if it uses pure metal, the resistance will increase. When resistance increase based on Ohm's law, the current should drop. When the current drop means what? Your phone starts to become slower, the lighting becomes dimmer, all right? And then it will go until no battery. That is something that we don't want in our technology, our era right now. All right, so that's metal. For insulators, they are poor conductor of electricity because they have very few free electrons to move around. All right, their electrons are usually bound to other covalent bonds. Okay, so the resistance of insulator is very, very high. So what to do last time? They only have metals and insulators. Then after that, they found semiconductor. When they found semiconductor, they noticed that semiconductor's electricity conductivity is actually in between conductor and insulator. Meaning means it is a moderate conductor of electricity. One, the resistance of semiconductor is in the middle of conductor and insulator, which means higher than metal but lower than insulator. So semiconductor of pure elements are silicon and germanium. Okay, so what's so good about semiconductor? At 0 Kelvin, very cold temperature or very high temperature, semiconductor actually acts as an insulator, which means the resistance at very cold temperature is high. And when the temperature increases, the conductivity of the electricity will increase because the resistance can be lowered. In another words to say is that semiconductors resistance can be changed. All right, but metal's resistance it changed based on temperature also, but not as much as semiconductor. All right, so an example of a semiconductor is like this. This is a silicon. Now we're going to focus on, let's see, one, two, three. Okay, we're going to focus on the slides back again. Please bear with me. My head has too many jumble up notes right now in my head in physics right now. Okay, charge carriers. Electricity conductivity in semiconductor occurs because there's two types of charge carrier. If we recall the definition of current, all right, the definition of current is rate of charge. Ayo. Rate of charge flowing in the conductor. So, but if you recall, it wasn't specified whether that charge is a positive charge or a negative charge. Main reason is they don't really bother whether it's positive charge that's flowing or negative charge that's flowing. So over here, what happens is in electricity, there's two types of charge carrier. Charge carrier means what causes the current to flow. Okay, so first we have free electrons. Free electrons means that particular metal has a lot of free flowing electrons around, and this free flowing electrons will actually be the negative charge carrier. When they have more electrons, that atom is negatively charged. So that is the negative charge carrier, and hence that is what we call the N type of semiconductor later on. All right, holes, if you were recalling the simulations that I did during the Bankill the other day with, who was it, Chirong, is it, whereby if there's a chair, okay, let's just say there are chairs over here. I remember using Chirong and asking Chirong to stand up that day. Okay, now, so over here, let's just say if I have a person sitting here and another one here and another one here. Okay, so this empty position, this is actually what we call a hole. It allows electron to sit there, but currently right now there's no electrons. So when there's no electrons, and then let's just say here is positively charged. This is the positive terminal of the power supply, and here's the negative terminal power supply. So the negative terminal power supply will repel the electrons, and the electrons will be attracted towards the positive terminal. So what happens here is that because positive is on the left, gonna focus over here. All right, positive is on the left, and what happens is this particular the electrons, all right, it will be attracted towards the positive terminal, but here got empty space already, so what will happen is this electron will move, and when it moves, the holes actually move towards the right hand side, whereby the electrons move towards the left hand side, and they will actually cause the current to move. Okay, so this is actually holes, which is positively charged. All right, so I hope it explains about positive and negative charge carrier. Negative charge carriers are free electrons. Positive charge carriers are holes, which means uh, atoms with insufficient electrons. Okay, all right. So can we continue? Are you guys okay to continue? Dun, dun, dun. No. All right, let's continue a little bit more before me taking a break as usual. All right, now silicon atoms. Silicon atoms are actually atoms with 4 electron valence. All right, silicon atoms are electrons with atom with 4 electron valence at the outermost shell. All right, so usually these 4 electrons they will be shared by 4 other neighboring atoms. Why is this so? Okay. All right, it will be shared by 4 neighboring atoms, 4 neighboring silicon atoms also, to form 4 covalent bonds. So what happens here is that all these are silicon atoms, all right, and then they have 4 electron valence, and they share the electrons with 4 other electrons also, the other silicon as well. So what happens here is that what you see is that it shows that the outer electrons in the silicon crystal, which are involved with a perfect covalent bonds, leaving no free electrons to conduct electricity. Silicon is a semiconductor, all right? And semiconductor here is that at low temperature, the pure silicon crystal in an insulator has high resistance. Why high resistance? Because all of them are in a perfect covalent bond. All 4 of the electron valence are in perfect covalent bond, and hence at very low temperature, they are all in the covalent bond. There's no free electrons moving around. There's no holes moving around. So at low temperature, pure silicon is an insulator with high resistance and low current. So no current will flow. Okay? But as the temperature increases, electrons, the energy of the vibrating atom, because when the temperature starts to increase, the electrons atoms will actually start to vibrate. So when it starts to vibrate, some of the electrons starts to break free. And when it starts to break free, it can move towards the positive terminal, hence reducing the resistance. All right. So every electrons that is broken free, there is a hole in the bonding structure. Okay. So later I'll show you the simulations. This hole will be the positive charge carrier, and the electrons that break free is the negative charge carrier. Okay. So when there is holes, the electrons will start to move. All right. From one covalent bond, it will actually move to another one towards the positive terminal. All right. The main purpose is the electrons wants to go towards the positive terminal. All right. So this is the physical origin of the increase of the electrical conductivity. All right. So this is actually the pure silicons. Let's see any simulation that we can look at. All right. This is for silicon. All right, and we have all the silicon sets actually merging. So at pure silicon, it actually is a perfect covalent bond over here. All right, so this is where the electrons, they have 4 electrons, and then all of it is actually at a perfect covalent bond. So there is no electrons, but as temperature increase, the some of the electrons will break free. And when it breaks free, other electrons will try to jump into that hole. It's like musical chair. All right, they are trying to fight for the empty space. Okay, this one sudah habis. Let's see. So like for example over here, I saw the simulation and then suddenly simulation tak dapat bergerak. Something wrong with the simulation. Okay, then we're gonna ignore that. Okay, so pure silicon, if it's the temperature increases, then only the electrons will break free. Electrons, when it break free, all right, if this is the positive terminal and over here is the negative, electrons will actually move towards the positive terminal. The hole will move towards negative terminal. All right, so that is the origin of our diodes. Okay, the basic one of all that's semiconductor for silicon. All right, so I'm gonna take a break for a while. So the rest of you have to take a break. I need to have a rest of my head before I go into the doping process. All right, so let's just take a quick break of 5 minutes, and we'll be back in 5 minutes time. Right?